Yes, it's some kind of guy. In this video, we are going to talk about prostaglandin and leukotriene synthesis. We want to know what are they, their roles, where are they found, and also talk about different drugs which act at different sites of their synthesis, and also the agonists and antagonists of different metabolites. Don't worry about the structures. These structures will help us to really understand the concept very well. Please don't forget to subscribe, like the video, and share. Let's go. What are prostaglandins? Prostaglandins were first isolated in semen, and they realized that semen could contract isolated uterus and other smooth muscles. So the active in the semen was termed as prostaglandin, thinking that it was from the prostate gland. Leukotrienes, they are called leukotrienes because they are first isolated from the leukocytes, and trienes because they have 3 conjugate double bonds. When I talk about the conjugate double bonds, it's a double bond, single bond, double bond, single bond. So they have 3 conjugated double bonds. This is the conjugate system. So this is double bond, single bond, double bond, single bond, double bond. 3 of them, as we are going to see. For example, we have this structure. This is a leukotriene because it has 3 conjugated double bonds. This one, then single bond, double bond, single bond, double bond, like that. Those are leukotrienes. Prostaglandins are synthesized from different fatty acids, but mainly from arachidonic acid. Arachidonic acid, this is arachidonic acid. It's the main precursor of these prostaglandins. How is it synthesized? This arachidonic acid is gotten from diet. Or from dietary linoleic acid. When it reaches the plasma membrane, it is esterified. This is an ester, mainly as lecithin. By the help of enzymes, that is phospholipase A2. Phospholipase A2. It cleaves at this position here. Phospholipase A2. Then we get the arachidonic acid. This is through the stimulants. For example, the growth factors, and cytokines. These, they are the stimulants which leads to the production of the phospholipase A2. This cleaves the esterified arachidonic acid to get the arachidonic acid. Then, this arachidonic acid is the precursor of all these prostaglandins. It's the main precursor. Now, from the prostaglandin, from the arachidonic acid, by the help of different enzymes, we have 2 pathways. We have the LOX pathway and the COX pathway. The COX pathway provides us with the cyclized prostaglandins, or they are called prostanoids. Why are they called prostanoids? It is from the hypothetical compound known as the prostanoic acid. This compound. This is the prostanoic acid. It has a cyclic pentane. This is the cyclic pentane ring, this ring here. So you can see that all of them, they have this ring. So they are called prostanoids. This COX pathway, we have 2 types of COX enzymes. We have COX-1 and COX-2. Both of them can produce these compounds, as we are going to see. This is called the COX enzyme, this one, or it's called the prostaglandin endoperoxide synthase. This enzyme, it has two active sites. We have COX active site. This side, we have the COX active site or the cyclooxygenase active site. And this side, we have the peroxide active site. When you get the arachidonic acid, it is cyclized to form this prostaglandin G2. This prostaglandin G2, after being cyclized, then it will be cleaved. This is the peroxide part. This is the peroxide part. It will be cleaved to prostaglandin H2 by the peroxide or the peroxidase active site. It cleaves the peroxide region, this part. But these two, they still have the peroxide here at the ring. We have a peroxide and a peroxide. So these two prostaglandins, they are called the cyclic peroxides. After the synthesis of prostaglandin G2, then it is cleaved to prostaglandin H2. This prostaglandin H2 now will give us all other prostaglandins, as we are going to see. This is prostaglandin E2. Why are they named like this? Prostaglandin A, B, C, D. It is due to different substitutes at the cyclic ring. At cyclic rings, because you are going to see that the side chains, all these side chains, they're almost the same, but the difference is at the ring. It's at this ring. So this is prostaglandin E2. It has a ketone here and hydroxyl group. Then we have prostaglandin F2 alpha. It's called prostaglandin F2 alpha because these hydroxyl groups, they are at the same side of the plane. If this is a plane, this one shows that they are at the other side of the board. And okay, also here we have two chains. We have this chain and this chain. This chain shows that it is above the plane. Then this one shows that it is behind the plane. So all of them, they have this conformation or this orientation. They have this orientation. This is alpha and this is beta. They are at different sides of the planes. So this one shows that these ones are at the same sides. So the hydroxyl group is due to being at the same side, so it is F2 alpha. Here, this is prostaglandin D2. Prostaglandin D2, it looks similar to prostaglandin F2, but I mean to prostaglandin E2. But the difference, the OH here is at this position, but here it is at this position. This is position 1, this is 2, we have 3, 4, 5, 6, 7, this is 8, this is position 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the positions matter. So this is position 9, but here hydroxyl group is at position 11. So that's the difference. Now, here we have different enzymes. Here we shall have prostaglandin prostaglandin endoperoxide E isomerase for the synthesis of prostaglandin E2. Here we shall have prostaglandin endoperoxide reductase for the synthesis of prostaglandin F2 alpha. Then for prostaglandin D, we have glutathione S synthase. So those are the enzymes. We are going to see the different agonists and antagonists of these prostaglandins. And prostaglandins have different activities depending on the tissues where they are found. That all tissues, they have COX enzymes, but the further course of the synthesis of these other prostaglandins depends on the different enzymes present in a particular tissue. Here, from prostaglandin H2, again we form thromboxane. This is thromboxane. This is thromboxane A2. By thromboxane A2 has short half-life that's converted to thromboxane B2. This one is inactive, but this one is active. This thromboxane A2, it is formed by the enzyme which is thromboxane synthase. Thromboxane synthase gives us the thromboxane A2. Why are they called the thromboxane? It's because of this ring. This ring, the oxygen ring, the 6-membered ring with oxygen. And you see that then this oxygen atom is at this position. This is position 9. This is position 11. They form this ring. There's another ring here which is a 4-membered ring. This oxygen is at the other side of the board, as you can see. These dotted lines. Then for prostacyclin, this is prostacyclin or prostaglandin GI2. Also, you can see that we have prostaglandin G2, H2, E2, F2, D2. Why are they called so? It's because at the side chains we have 2 double bonds of the side chains. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So they are called prostaglandins A2, B2, like that, G2. But we have no prostaglandin A2, B2, or C2 because they are not natural prostaglandins. They are not synthesized in the body. You can see that arachidonic acid has 4 double bonds. But due to cyclization, the 2 bonds are saturated. Then we remain with only 2 bonds of the side chains. So we shall have the A2, B2, C2, which is not the case for the leukotrienes. For leukotrienes, there is no cyclization. So they remain with their 4 bonds, their 4 double bonds. Then prostaglandin G2 is synthesized by the enzyme called prostacyclin or the prostaglandin I2. The enzyme is called prostacyclin synthase. This prostacyclin synthase provides prostaglandin I2 or the prostacyclin. Why is it called prostacyclin? It's due to the addition of the ring. We added another ring. We used carbon, this carbon 7 and this oxygen here. They formed a bond. This carbon 7, this is 7 and this is 6. 6 and 7. They combine with this oxygen to form another ring. So they are called prostacyclins. Then this prostacyclin or the prostaglandin I2 provides the, now here we have a ketone at position 6. So this one will be called the 6 keto. Then prostaglandin. Now here it was prostacyclin, but here to be prostaglandin F1 alpha. Is F1 alpha because we have only one double bond here and the OH groups they are at alpha position. So we have prostaglandin F1 alpha. Then this is the COX pathway. Now when you go to the LOX or the lipoxygenase pathway, this is lipoxygenase pathway. This is the COX pathway. Now here we form the leukotrienes and other compounds with the help of the 5 LOX here, the 5 lipoxygenase, in the presence of the enzyme known as FLAP. This is 5 lipoxygenase activating protein. This protein gets the arachidonic acid and takes it to the 5 lipoxygenase. This one converts it to the 5 heptane. This is hydroperoxide eicosanoic acid. They have tetra because you can see that here there is a double bond also. They have 4 double bonds. We have 4 double bonds, so they are called eicosanoic acids. These are fatty acids. Now, this one will be converted to leukotriene, the leukotriene F4. They are called trienes because they have 3 conjugate double bonds, but they have 4 double bonds, but 3 of them they are conjugate. You can see double bond, single bond, double bond, single bond, double bond. But here we have single bond, single bond. So this one is not part of the conjugate system, but there are 4 double bonds. So they are tetraenoic acids. But 3 conjugate double bonds makes them to be called leukotrienes. So this one is not a leukotriene, but this one is a leukotriene now. Because here we have only 2 conjugate double bonds. Now, this leukotriene F4, they are called F4 because we have 4 double bonds. As we say that here, for the COX pathway, there is cyclization, we lose 2 double bonds. But here, there is no cyclization, so we retain all the 4 double bonds. Then, this F4 gives us the leukotriene B4. Then, B4 also we get from F4 we get the leukotriene C4. Leukotriene C4 will give us these other leukotrienes, but the difference will be here at our position. So these ones are called cysteine prostaglandin. Cysteine leukotrienes, because of this S group here. Now, D4, we shall get E4. From E4, we get F4. These are leukotrienes. This is leukotriene B4. So this is 5 LOX. Why is it called 5-lipoxygenase? Because when you count, this is 1, 2, 3, 4, 5. At 5th position, there's formation of peroxide here. Then it is cleaved, and from here we get other leukotrienes. Then this one is called 12 LOX, the enzyme 12-lipoxygenase, because the activities are at 12th position. So we shall get this 12 heptane. There is this P because of the peroxide. You have a peroxide at position 12. So it is hydroperoxide eicosapentaenoic acid. Then from here we see that it is cleaved, remain with OH group. So this one is called 12 heptane now. Heptane. Hydroxy eicosapentaenoic acid at position 12. Then we have another enzyme to be called 15 LOX. 15 LOX will provide us with 15 heptane and lipoxins. These lipoxins, for them, they are anti-inflammatory. They are anti-inflammatory, but we shall see that for the leukotrienes, they are inflammatory, and these other prostaglandins can be produced due to inflammation. Now, prostaglandins, they are, most of them, they are always there in the body. The presence of COX-1, this COX-1 is a constitutive enzyme. It's always there in most tissues. For example, in GIT, it leads to the production of glucose, inhibit the production of the gastrin and gastric acid, such that it can protect the mucosal membrane. But for COX-2, its production can be induced, though it can be constitutive in some areas of the body, but its production can be induced. And when it is induced by the cytokines and growth factors or other pro-inflammatory substances, it can lead to production of its induction can lead to inflammation. If it is induced, can lead to inflammation. But you can see, or you can find that in some areas, such as in the kidney, in the brain, and in fetus, such as in ductus arteriosus, this COX-2 or COX-2 is always present. It is always present as a constitutive enzyme. It plays a role there, but its induction can lead to inflammation. Also, it is present in the blood vessels, endothelium of the blood vessels. Now, we say that COX-1 or COX-2, both of them can produce the prostaglandin G2 to prostaglandin H2, but further prostaglandins are produced due to different enzymes present in different tissues. For example, after the production of prostaglandin H2, these COX are present in all tissues, but these other enzymes, they are specific for different tissues. For example, the thromboxane, after production of prostaglandin H2 in platelets, this thromboxane is the main enzyme. So this thromboxane will be produced from thromboxane synthase. but this is mainly in the platelets. Mainly in the platelets. Then when it comes to the prostacyclin, this one is present constitutively mainly in the blood vessels, in the endothelium of the blood vessels, and also in the lymphatic tissue. This one mainly in the blood vessels, endothelium. Then the prostaglandin E2 and F2 alpha, then D2, they are also present mainly in different tissues, but also in the mucosa of the GIT. You can find that some tissues can produce all the prostaglandins and leukotrienes. For example, the lungs and spleen. The lungs and spleen can produce the leukotrienes and the prostaglandins. You can find that these leukotrienes, they are produced much more in the asthmatic patients. So let's talk about the different drugs where they act at different sites.